the next stage what we want is to see, similar to the propositional logic, what are the laws that can be valid in the first order logic, right. So, we will be a bit greedy in the sense that knowing some laws in propositional logic, how to give analogous laws in the first order logic immediately instead of doing them separately, right. For example, we know P implies P is valid in propositional logic. So, does it imply that Px implies Px is also valid in first order logic? So, because anyway we are concerned with the patterns only, right. So, they are having the same pattern. Can we conclude from this, or we will have to go to semantics again and do it, right. So, this is the greedy approach we will be taking. So, from the laws of propositional logic itself, we can now formulate some laws for the first order logic, if this analogy really holds, right. But there you have the interpretations for the propositions. Now, in first order logic you have the states instead of the interpretations. So, how to connect those interpretations with the states, that first we have to see, right. So, if not everywhere, at least wherever that connection remains, we should be able to go for the first order logic, right. So, basically it is like, suppose you have one interpretation in propositional logic, right. So, of any proposition it can be either evaluating to 1 or 0. So, let us say it can be there true or it can be false. Now, when you take one state corresponding to this interpretation, the state similarly should hold for whatever formula we want to substitute in place of that proposition, right. For example, we take this M, P implies P, say P implies P is valid, we know, right. Instead of this small p, I want to write Px. So, I would get Px implies Px, fine. Now, I consider a state which will be same thing or evaluating the same way to this as the interpretation evaluates P implies P. Then immediately we can say that interpretation satisfies this if and only if this state satisfies this. That is what we want to preserve first, right. So, what we propose is, suppose I have a proposition and Px a formula. So, in some way I am identifying this P with this Px, I have a map, let us say, right. Informally we can write this way, it says that you have some map, for each proposition it gives some formula there, right. So, for small p I have this Px, okay. So, now what I do, suppose I is an interpretation, I is an interpretation. So, this is in the sense of PL, okay. So, let us write PL interpretation instead of just interpretation. And similarly, let us take IL a state. So, they are in such a way connected that whenever I of this P is 1, I have IL satisfies Px. Okay. Now, what I do? I take any formula, let us say x. In x there can be p's, suppose there are some small p's occurring in x. Then in all those places wherever this small p is occurring, we want to substitute Px instead, right. So, let us say let x be a formula, but we want to start from the propositions like P implies P. So, we will not take in general any formula, but let us start with the proposition where small p occurs, okay. Let x be a proposition denote by x p substituted by, let us say, Px, the formula obtained from x by replacing each occurrence of p with p x. Okay. So, now what happens? X p substituted with p x has no variable capture, right, because we have started with x as a proposition itself, there is no quantifiers, right. So, things are simplified here, there is no variable capture is occurring, fine. Now, with that what we want to say is, since I and IL are connected the same way, it small I satisfies small p if and only if IL satisfies p x. So, what we expect is x is satisfied by that I if and only if x p equal to p x is also satisfied that IL, right, that is what we want to say. So, if I satisfies x, then IL must satisfy p x, not p x, it is x p substituted with p x. And conversely also, right. Similarly, if IL satisfies this new formula, then I should satisfy x. Okay. In fact, it is not limited to such atomic formulas as p x, we can take any other formula also, that should also work, right. So, let us do that, let p be a proposition and identify any formula corresponding to this p, fine. So, let us write it as x subscript p instead of p x. So, everywhere we should be able to substitute that, replace this p x by x p. So, let us substitute. This is what we expect to hold. So, it is really number of occurrences of connectives, right. So, we wrote occurring here, but you can make it better. So, suppose in the basis step what will happen, this number of occurrences of connectives is 0, fine. So, basis step, if this number is 0, then how does it look like? It can be top, or it can be bottom, or it can be a propositional variable, fine. That is how propositions have been formed. So, once this happens, you will get correspondingly x p replaced by x p as top or bottom or p x. So, here it is x p. Okay. Now, the things are clear, because the assumption says I satisfies p if and only if IL satisfies x p, right. So, the conclusion and the assumption they are the same here. Conclusion is also the same thing, I satisfies p if and only if IL satisfies x, p replaced by x p, which is now x p, fine. So, basis case is clear. Now, in the induction step, what do you do? So, you can say x can be in the form not of some y, or y and z, or y or z, or y implies z, or y biconditional z. These are the possibilities. Let us take the first case, say y x equal to not y, x equal to not y. Then in this case x p replaced by x p would give not y p replaced by x p. Okay. Fine. Now by induction hypothesis there is one connective less here. So you do it exactly how to do. Induction hypothesis is for number of connectives less than or equal to m, the conclusion holds. Now it has m plus 1 connectives. Then this y has number of connectives less than or equal to m. Therefore you can use the induction hypothesis. So that says I satisfies p if and only if IL satisfies, sorry, I satisfies y if and only if IL satisfies y p substituted by xp, right. This is what the induction hypothesis says. So I satisfies y if and only if IL satisfies y p replaced by xp. Now conclusion is clear, right, because the connective not. The same way also IL tackles not as I. Is that clear? Now for all the connectives proof will be similar. You just go on writing it, that is all. Fine. So let us call it our first lemma for substitution. Now the main theorem you can write easily, where you need not connect I and IL, you have to go for validity, let us say. Fine. So we can write now on the uniform substitution. In a tautology. So we are telling valid propositions in PL also. Here also we are telling valid formulas. So this valid might confuse. We will say in FL if you take a proposition which is valid, we will call it a tautology, right. While considering both PL and FL, we will say valid propositions as tautologies, right. So that we will not have any conflict of terminology. This is what it says, uniform substitution in a PL valid proposition. Instead of telling PL valid proposition, we are making it tautology. So now it says that if you start with a tautology and then replace each occurrence of a propositional variable by another identified formula xp, then whatever you get from that, that will also preserve validity, right. So you have to only write it, if x is a tautology, then x where p is substituted by xp is valid. To write with every detail, we have to go to this first portion of the lemma. Let p be a proposition, identify xp, a formula corresponding to this p, then denote by x p equal to xp the formula obtained from x by replacing each occurrence of p with xp, then right. Whenever x is a tautology, p x where p is substituted by xp is also valid, right. Proof is clear. Is there anything to do? Yes, is it clear or not? Not clear? Okay. X is a tautology, so that means you take any interpretation, it satisfies it. Okay. Now what do? You take any state x p equal to xp. Okay. In this state, what will happen? this small p is either evaluated to 1 or 0, right. Whatever way it is evaluated, you find out which I is that. Is it okay? See, this is the way we will be proceeding. Suppose x is a tautology. We want to show that x p replaced by x p is valid. So, let I L be a state. Okay. Now, I L satisfies x p, it is a model of that, or it is not a state model of that, right. So, define on interpretation I or on a PL interpretation I by what you do, I of p equal to 1 if I L satisfies x p. It either satisfies or it does not satisfy, right, or it can happen it does not satisfy. In that case, you put I p equal to 0. Either I L satisfies x p or it does not satisfy x p, right. So, whatever is the case, do that. Okay. Now, then apply the lemma, that is all, proof is over. Okay. So, once it is a tautology, each I evaluates it to 1, right. By the lemma, each I L will also evaluate to 1. Clear? So, this is called uniform substitution in a tautology. There is again another type of uniform substitution. See, if you have started with tautology, you are ending with valid propositions. Now, instead of starting with tautology, in FL, suppose you have valid formulas, can you substitute there itself instead of from the proposition, right. So, that will mention as uniform substitution. We are not starting with any tautology here, it can be any valid formulas, fine. Our thing is that we assume or we presume that it should go correctly. So, whatever formula you are getting after the substitution should also be valid, right, but there can be a problem, there can be some problem there. It is the variable capturing. Suppose you start with one formula in this form, x equal to p implies for each x p, that is allowed in FL as a formula, right. This is a proposition. So, proposition is a zero or predicate. Before that predicate, you can always use one quantification for all x, though it is vacuous, this x does not occur there, but it is still allowed. Now, what happens if you substitute this p by xp or say px? So, this will be equal to px implies for each x px. Now, variable is captured. When variable is being captured, I have just substituted this p by px. Formally, this is how substitution will work, right. So, what I get from this is px implies for each x px. This is not valid, right. Is that okay? Like you take one state where x becomes 2, okay. P means prime. So, in the set of natural numbers, it will say 2 is prime implies every natural number is prime, which is false, right. So, this is not valid, though where from we have started is valid, because there is no x there. So, it is vacuous, it does not matter whether x is there or not, that is valid. Okay. So, you should have some constant on the capturing of the variables once you generalize it to valid propositions or valid formulas. Okay. So, that is exactly the proviso, that is exactly the constraint we need. Fine. So, let us formulate the theorem. Uniform substitution. So, we start with let x be a formula, p a propositional variable, then x p a formula corresponding to or identifier to correspond to this p. In fact, this is only for our mention, formula is enough. This is what we are going to do, right. Then denote by x p substituted by x p as earlier, right, by or the formula obtained from x by replacing each occurrence of p with x p, right. So, now we need something more, we have to give our constant, right. Suppose no free variable of x p becomes bound or is bound really in x p replaced by x p. This is the condition we need. If x is valid, then x p replaced by x p is also valid. Okay. Again proof will be similar, but you have to formulate first its lemma, then proceed. So, the same proof almost will work, because corresponding to each I you will get one I L which are so related. P is satisfied whenever that x p is also satisfied in the corresponding state model, and then proceed. In proving that lemma, now induction hypothesis or induction step will involve one more thing, that whenever you started with your x, that can have a quantifier. Earlier it was a proposition, so you had no quantifier. Now, when you start with x itself, there can be quantifiers. So, two more cases will come, right, that x is in the form for each x y or there is x y. In that place you will need this proviso to prove it, okay, that you can do exercise. So, these are the two things which will be useful in getting many more theorems from the propositional logic first and then from the first order logic itself. Okay. There is another kind of replacement which we had done earlier, which is the equivalent substitution. When if something is equivalent to another, you can always replace it, preserving equivalence. So, let us formulate it first. Let A and B be formulas, X a formula. So, what we want to say is that if A is equivalent to B, then in X you replace these occurrences of A and B, right. You should end with some equivalent formula, that is what it says. So, suppose A is equivalent to B, denote by x, A equivalent is substituted by B, okay. One subscript we give now. The formula obtained from x by replacing each, but do we need each occurrence here now? They are equivalent, even some will do. So, write each or no or some occurrences of A by B in X. Okay. So, what we conclude is X should be equivalent to the new formula, or you say the new formula is equivalent to the old one. Fine. So, proof is again conceptual, there is nothing much to it. So, when you say A is equivalent to B, right, you take any state model or any state, then in that state whenever A is satisfied, B is also satisfied, and conversely, that is the meaning of equivalence. Okay. Now, let us start with any state I L. We want to find out whether I L satisfies this new formula or not, or even the old formula, let us say I L satisfies X or not. Okay. Now, how do you find out whether I L satisfies X or not? Go for our scheme. Our formal semantics simply reduces satisfaction to the level of satisfaction by a predicate, right. Is this clear conceptually or not? Suppose I have a formula X which looks like P x implies P x for simplicity. Now, let us say whether I L, we want to find out whether I L satisfies P x implies P x, right. So, how do we proceed? Our formal semantics asks us to do the following. We say I L satisfies P x implies P x if, next step is we will use the semantics of implies, that connective arrow. So, that says I L does not satisfy P x or I L satisfies P x, it will come to this, right. If it is something more, let us say for each x P x implies P x, this is what we want to do, then this step will be does not satisfy for each x P x or I L satisfies P x. So, there is one more thing to be done for the quantifier. So, we go next, we write if and only if for some D in our domain, right, what happens? I L x fixed to D does not satisfy P x, is that okay? For each x it does not satisfy, that means there is at least one element for which it does not hold, right. So, then what happens? We write this, then or I L satisfies P x. Okay. That is what we had done. So, finally, it is reduced to some state either satisfies that atomic formula or it does not satisfy atomic formula. It is reduced to that. Inside something for some, for all, or and something is written. Okay. So, we are now thinking that conceptually. Suppose I start with any state that satisfies X. So, my formal semantics says that I should go on writing types like this in our meta language English, right. Go on writing like this, finally, where something will be written P x not P x or something will come, okay. Atomic formulas will be coming. I L satisfies some atomic formulas or I L does not satisfy some atomic formulas with some, all, right. These kind of expressions will come there. Now, what happens? Whenever I L satisfies A is occurring there in that big reduction, I L satisfies A, you can simply replace I L satisfies B, okay, because A and B are equivalent. right. Now doing that, whenever whichever occurrence corresponding to the replacements A and B, you replace IL satisfies A as IL satisfies B, or IL does not satisfy A as IL does not satisfy B. Now you get a big expression like this, which will simply prove IL satisfies X, A replaced by B. That is the proof conceptually. The doubt is that we are not writing directly, if IL satisfies X, then IL satisfies X, P equal to XP. The reason is, I do not know how the interpretations of P and IL of XP are related. In your lemma, which you proved for substitution in a tautology, you had that connection, right. So it can happen that one interpretation satisfies P, but the corresponding state I am considering does not satisfy XP, right. So in the basis step itself it fails. Is it clear? But then to prove this uniform substitution, you have to start with a lemma with that constant corresponding to I of P. You first construct IL, the corresponding IL, which will behave the same way with XP, fine. But anyway, ultimately our result is this, which we will be using, not for any particular state, right, validity or satisfactory, that is what we want. So similarly here you are starting with A equivalently replaced by B, and it goes to the level of states, but since A is equivalent to B, always you can write IL satisfies that, IL does not satisfy that as it is, fine. So proving or formulating another lemma is not required here because of the condition of equivalence. Is it clear? So these are the three substitution theorem which we will be using to obtaining many more laws from the propositional logic and also from the first order logic, right. Let us see some examples. What are your laws in propositional logic? One is the example we have already given. Suppose I start with say Clavier's laws, so which says not P implies P, therefore P, right. This is what it says, fine. Now the same thing I can now write in first order logic, which will look like whatever be the formula X, it will say X implies X, from this you can conclude X. Now X is any formula, right. If you have taken X as Px, you would get Pxy implies Pxy, this implies Pxy, this is valid, okay. And with a lot of infinitely many, so it is a law, replace this X by any formula. So now you can translate or rewrite all those laws from PL to FL, whatever you did, we are not going to write them again. Now there are three theorems in propositional logic, we want to see whether those things still hold or not. For example, your deduction theorem, if you apply deduction theorem here in propositional logic, it will look like not P implies P, therefore P, right. You can take it as a consequence, fine. Now also it will come as not X implies X and also X, but then you have used deduction theorem. This part is easy because modus ponens. The other side, from this to conclude not P implies P is valid, is really your main part of the deduction theorem, right. So now the question is whether deduction theorem holds in FL, whether monotonicity holds, whether reductio ad absurdum holds. In FL, right. So, let us see monotonicity. How does it look like? So, it says suppose sigma is a subset of gamma sets of propositions. Now, you will write sets of formulas, right, FL formulas, and then let us take another, say X is a formula, be a formula. So, it says if sigma entails gamma, sigma entails X, then gamma also entails X. Okay. And there is another part, it says if gamma is satisfiable, then sigma is satisfiable. Since gamma is satisfiable, it has a state model. So, you have to start with a state. So, let IL be a state. So, when we say IL is a state, we are not writing all the details. We should have written first I equal to d phi is an interpretation, then let L be a valuation under this interpretation, so that IL becomes a state. So, all these things are assumed here. Fine. So, suppose IL is a state. Now, then what we say that if IL satisfies gamma, then what happens? By definition, IL is a state model of each proposition in gamma or each formula in gamma now, right. So, just the detail I have to write, IL is a state model of each formula in gamma. Now, sigma is a subset of gamma. So, IL is a state model, just very mechanical, of each formula in sigma. Right. So, this says any state model of gamma is also a state model of sigma, that much is enough. Those two propositions are reformulation of this. Okay. So, it directly proves that if gamma is satisfiable, then so is sigma. Right. If it is satisfiable, IL satisfies it, therefore, IL satisfies sigma, therefore, sigma is satisfiable. Okay. So, second thing, if sigma entails X, now the other one, if sigma entails X, then whenever IL is a model of sigma, it is also a, that is not it, we will say IL is also a state model of X. This is given. We want to prove gamma entails X. So, we start with a state model of gamma. But we have already shown any state model of gamma is a state model of sigma. So, IL satisfies sigma. Now, since sigma entails X, IL satisfies X, that is the end of the proof. Okay. So, monotonicity is easy. And now, you see, if you have taken just small I as in propositional logic instead of this IL, is it not the same proof as that of propositional logic? So, it is really propositional in that sense. The proof is also propositional, it does not go to the detail of quantifiers. Okay? Because state models perform the same way as interpretations in propositional logic. Then what about reduction or upside down or deduction theorem? Just we have to formulate it. So, let sigma be a set of formulas x a formula, then it says sigma entails x if and only if sigma union not x is unsatisfiable. Also another formulation, sigma entails not x if and only if sigma union x is unsatisfiable. Okay, now what happens here? First one, let us say, so sigma entails x, you want to prove sigma union not x is unsatisfiable. So, first suppose sigma entails x. To show sigma union not x is unsatisfiable, how do we proceed? So, let IL be a state. If IL satisfies sigma, there are two cases, IL satisfies sigma or IL does not satisfy sigma. So, if IL does not satisfy sigma, then there is nothing, IL does not satisfy sigma union not x also, whatever that IL may be, monotonicity, right. So, this becomes unsatisfiable. What about first one? So, let us complete that. Then IL does not satisfy sigma union x either. Okay. This is what it is telling. Okay. In this case, what happens? If IL satisfies sigma, then since sigma entails x, IL satisfies x, right. So, IL does not satisfy not x. Okay. So, IL is not a state model of sigma union not x. Is that okay? So, now is it clear? First one, if IL satisfies sigma, then IL satisfies x because sigma entails x, right. Now, IL does not satisfy not x because of connective not. By monotonicity, IL does not satisfy sigma union not x, and also by definition, because not x belongs to sigma union not x. So, one of them it does not satisfy, therefore, it does not satisfy the set, fine. On the other hand, suppose IL does not satisfy sigma, then IL does not satisfy sigma union x, because in sigma there is one which it does not satisfy. So, also sigma union x, but we need sigma union not x. Let us take not x, any set we could have taken, fine, sigma union not x, right. So, in any case, whatever state IL you start with, it does not satisfy sigma union not x. Now, give that argument, not before it. Therefore, sigma union not x is unsatisfiable. Is it clear? So, this says IL does not satisfy sigma union not x, whatever be this IL. So, sigma union not x is unsatisfiable. Okay. So, conversely what you do? Conversely, suppose sigma union not x is unsatisfiable. So, again there can be two cases, IL satisfies sigma or IL does not satisfy sigma. If IL does not satisfy sigma, then what happens? So, all those IL, for all those IL, the statement if IL satisfies sigma, then IL satisfies X is true vacuously, right. That is what we want, sigma entails X, fine. So, when IL does not satisfy sigma, then if IL satisfies sigma, then IL satisfies X is vacuously true. Okay. In this case, when IL satisfies sigma, we know that IL does not satisfy sigma union not X, because sigma union not X is unsatisfiable. Therefore, this IL must falsify not X, at least one of them is falsified, right, but all of in sigma are satisfied. So, the other one is falsified, right. So, this means IL falsifies not X, therefore, IL satisfies X, that is what we wanted. Is that clear? So, that means if IL is a model state model of sigma, then IL is a state model of X is satisfied, that sentence is true. In both the cases that sentence is true, therefore, sigma entails X. Is it clear? So, the same proof will hold for the second one also. What you have to do is replace every occurrence of X not having not there with not X, and every occurrence of not X as X. Simultaneously you replace X by not X and not X by X, right, simultaneously in this proof itself. So, you get the proof for the second one, fine. Now, deduction theorem you can prove similarly, they are also propositional. This is really propositional proof, we have not done anything with IL, you could have started with any interpretation itself, fine.